In my previous few videos, I have discussed the concept of reciprocal lattice in very detail, and I hope you have definitely watched all those videos in which I have given the different aspects, different properties of reciprocal lattice in very detail. Now today our aim is to discuss the most important law which is essential tool to study the X-ray diffraction, which is called Bragg's law in terms of reciprocal lattice. Actually, in this lecture we will also see the vector form of Bragg's law, and actually the vector form of Bragg's law, which is actually in terms of the reciprocal lattice vector, that is vividly used in construction of the Brillouin zones, which is a very important concept of solid state physics and crystallography. And in this discussion you will also learn about a very important geometrical construction which is called Ewald construction. Okay, so this lecture is very important. We will see so many aspects, so many concepts in this lecture. So first of all, let us learn about the Bragg's law in reciprocal lattice. As you know, Bragg's diffraction condition, which we have discussed already earlier, by considering the reflection of X-rays from parallel lattice planes. Actually, this law, which is expressed like this, 2d sine theta equal to n lambda. This is the mathematical form which is very simple of Bragg's law. Okay, and as you know that this law can be used to express the geometrical relationship between the vectors in the reciprocal lattice. Okay, and how we can express this Bragg's law, how we can actually relate the geometrical relation between the different vectors in reciprocal lattice using this Bragg's law, you will see in this lecture. And for this, let us see this figure which I have drawn here. Actually, in this figure I have shown the reciprocal lattice. All dots in this figure represent the reciprocal lattice point. Okay, now let us consider a point A, as you can see in this figure here. And this point A is not necessarily at any reciprocal lattice point. It may be at a reciprocal lattice point, or it may not be on a reciprocal lattice point. Okay, so let us take this point A, and taking this point A, let us draw a vector, as you can see in this figure, which is AO. This AO is a vector which I have drawn, and the terminating point of this vector I have taken here is O. Okay, and this O is the origin of the reciprocal lattice. So you can treat this point O as origin of the reciprocal lattice. RL I have written, which represents reciprocal lattice. Okay, now the length of this vector, that is vector AO, where O is treated as the origin of the reciprocal lattice, let us take it equal to 1 over lambda. Okay, it means AO is equal to 1 over lambda, where lambda is the wavelength of the X-ray. Okay, and we consider the direction of this AO along the direction of the incident X-ray. Okay, now taking this point A as a center and 1 over lambda as a radius, that is AO as radius. Let us draw a sphere which you can see in this figure. I have shown this sphere as you can see, and the center of this sphere is at point A, and its radius is AO, which is equal to 1 over lambda. Okay. And you can see in this figure that there is a point B here, which is lying on the surface of this sphere. Or in other words, you can say that this sphere, which has been drawn by taking A as the center and AO as a radius, this intersects some point B and of the reciprocal lattice. Okay. And so you can say that point B is a reciprocal lattice point. And since O is the origin, so the line OB, which joins this reciprocal lattice point B with the origin, that OB will represent a reciprocal lattice vector. So this is a reciprocal lattice vector. RLV means reciprocal lattice vector. Okay. Now you can see the figure. I have considered that the coordinates of this point B are H prime, K prime and L prime. It means I have considered that H prime, K prime and L prime, these are the coordinates of point B. Okay. And these coordinates have a highest common factor, let us say n. When you say that the coordinates H dashed, K dashed, L dashed have a highest common factor which is equal to n, what does it mean? It means these coordinates are of this form. It means the coordinates of point B are of the form NH, NK, comma, NL. Okay. Where actually H, K and L, these are all numbers, and these have no common factor greater than 1. It means if you want to define a common factor for the numbers H, K, L, that will be simply equal to 1. Okay. That will be simply equal to 1. Okay. So you can say that these HKL do not have a common factor other than unity. Okay. Now, as I have told you that since O is the origin of the reciprocal lattice and B is a reciprocal lattice point in this Fourier space, so this line OB or this vector OB, you should say, will be definitely the reciprocal lattice vector. Okay. And according to the definition, a reciprocal lattice vector must be normal to a plane formed by H prime, K prime and L prime. So you can say that this OB, which is the reciprocal lattice vector, that must be perpendicular to the plane H prime, K prime, L prime plane. It must be perpendicular to on this plane. Okay. Or you can also say that this OB should be perpendicular to the plane HKL. Okay. And according to the definition of reciprocal lattice vector, the length of this OB, it means modulus of OB, must be equal to reciprocal of the interplanar separation. And if you denote that interplanar separation by the symbol, let us say D H prime, K prime, L prime, then modulus of OB must be equal to 1 over D H prime, K prime, L prime. Or you can also say that this should be equal to n over dhkl, because instead of h prime, k prime and l prime, we have written here nh, nk, nl, and therefore in terms of the interplanar separation for the plane defined by the indices hkl, you should say that modulus of OB must be equal to n over dhkl, okay, n over dhkl. I think what I have explained here you have clearly understand, and for your convenience I have written all those things here. You can see, you can note down these facts which I have actually written here, and that will be a good notes for your examination purpose. Okay. Now again see this figure. Actually here I have shown in this figure that this B is a reciprocal lattice point, O is the origin of the reciprocal lattice, okay, and according to the definition of reciprocal lattice vector, OB is the reciprocal lattice vector, and so as the length of this reciprocal lattice vector must be the reciprocal of the interplanar separation, so modulus of OB must be equal to 1 over dh prime k prime l prime, or n over dhkl. Okay. But now see the geometry of this figure. As you can redraw this figure in this manner here. Let us see. I have shown here that AO is the direction of incident X-ray, okay, and this AE is one of such planes on which this reciprocal lattice vector is normal, okay, and let us say this point is A, okay, and this point is E, and this is your point O, okay. Now this is actually, this angle is 90 degree, and this angle is theta, okay, this angle is theta, and similarly you can see the triangle ABE, this is A, this is your point E, and this is B, okay. In fact, from geometry of figure it is clear that OE is equal to EB, OB is equal to EB, you can see, and this angle is again theta, and from here you can see that AO is equal to what? AO is equal to 1 over lambda, okay, and since point B is also lying on this sphere, so AB is also equal to 1 over lambda. And from the geometry of this figure, if you want to find the value of sine theta from any of these two triangles, you can see sine theta will be equal to what? That will be OE divided by OA or AB. And OA or AB, this is actually 1 over lambda, okay, and so this OE is equal to 1 over lambda times sine theta, okay, times sine theta, okay, but EB is also equal to OE, so this length of OE will be what? So OE, not OE but OB. OB will be simply equal to twice of OE, okay, twice of OE, and so this will be equal to 2 times OE is sine theta by lambda, so this is 2 sine theta divided by lambda, okay, 2 sine theta by lambda. But earlier, according to the definition of reciprocal lattice vector, we have defined that OB is equal to n over DHKL. So now we can easily equate the two values of OB. Okay, you can see that OB is equal to n by DHKL. So n over DHKL and 2 sine theta over lambda. 2 sine theta over lambda. These two should be equal because both defines the value of OB. And hence from here you can easily say that this 2 DHKL sine theta is equal to what? This equals n lambda. And what is this? You can see this is the conventional form of Bragg's law. So in this calculation, you can see easily that in terms of the reciprocal lattice, we can easily derive the Bragg's law. Okay. So this derivation is very simple, and I hope you have definitely understand how we can think about the derivation of Bragg's law in terms of the reciprocal lattice vector. Okay, you have definitely understand it. Okay, and again you can see actually all these calculations I have made here for your convenience. You can see I have shown this triangle here, and according to the geometry of figure, this OB is equal to n over DHKL, and from this geometry of figure, OB is equal to 2OE, and OE is equal to OA sine theta, and sine OA is 1 over lambda. So OB is 2 sine theta over lambda. Okay, and here according to the definition of reciprocal lattice vector, I have obtained that modulus of the reciprocal lattice vector OB is n over DHKL. And so you can now equate these two equations. So 2 sine theta by lambda is equal to n over DHKL, and this is 2 DHKL sine theta equal to n lambda. And this is the well-known Bragg's law, as you know. As you know, according to this law, this n actually represents the order of diffraction or order of reflection. You know, in Bragg's law, actually instead of the term diffraction, reflection was used. So you can say that this represents the nth order maxima, okay, or nth order diffraction or nth order reflection. Okay. In fact, as you can see, the coordinates of the reciprocal lattice point in this figure contain a common factor n. You have seen here the coordinate of this point B, which is actually h dashed, k dashed, and l dashed. I have written it nh, nk, and nl. So this actually these coordinates actually contain a common factor n. So if the coordinate of the reciprocal lattice point contains a common factor n, then this n has a particular meaning. Actually, this common factor n, which is a common factor of the coordinates of the reciprocal lattice point, actually that represents the nth order reflection from the plane HKL. Okay, from the plane HKL. Actually, this is also evident from the this geometrical construction that the Bragg's condition will be satisfied for a given wavelength lambda, provided the surface of radius 1 over lambda drawn about the point A intersects the point of the reciprocal lattice. Okay, Actually, this construction which I have made here, this is known as the Ewald construction. This is the well-known Ewald construction. Okay. So when you draw a sphere of radius equal which is equal to reciprocal of the wavelength of the incident radiation, and it intersects a reciprocal lattice point and satisfies the Bragg's law, then such a construction is called Ewald's construction. Okay. Now actually we are going to see the vector form of the Bragg's law, or you can say this is called the modified form of Bragg's law in reciprocal lattice space. Okay. In fact, Bragg's law itself takes a different form in the reciprocal lattice, which is actually called the vector form. Okay. So what is this vector form of Bragg's law? We will now see in this reciprocal lattice space. Actually, to obtain the modified form or the vector form of Bragg's law, now let us redraw the vectors AO, OB and AB. In the first figure, this you can see these are the vectors. This is vector AO, this is vector OB and this is AB. Now we will actually redraw these three vectors by magnifying their values by a particular factor, let us say 2 pi. It means we are just redrawing these three vectors by increasing their magnitudes by a factor 2 pi. So you can see that the new vectors are A prime O prime. See this figure. A prime O prime. This is the new vector for AO. The new vector for OB is O prime B prime. Okay. And for AB, this is A prime B prime. Actually, the magnitude of vector A prime O prime, A prime O prime, this is actually equal to 2 pi times of the magnitude of AO. Okay, magnitude of AO. And as you know that AO is equal to 1 over lambda, so this is actually equal to 2 pi over lambda. 2 pi over lambda. But you know that 2 pi over lambda, this is the wave vector. So in vector form, I have denoted this vector A prime O prime as the wave vector K. This actually represents the wave vector of the incident X-ray or incident radiation. Okay. Now the vector O prime B prime. This is the reciprocal lattice vector, as you know, and I have denoted this vector O prime B prime by the symbol G, which actually represents the reciprocal lattice vector. Okay. Now, as you know, the diffraction will occur only when the point B dashed must be on this Ewald sphere. So this is the necessary and sufficient condition for diffraction of X-ray to be taking place. So if the point B dashed also lie on the sphere, on the same sphere on which this O prime is located, only then diffraction of X-ray will take place. So you can say that the necessary condition for occurring diffraction is what? Is the point O prime and B prime must be lying on the surface of the same sphere. And if O prime and B prime both are on the surface of a sphere, of the same sphere, then definitely for this modulus of this A prime B prime must be equal to mod of A prime O prime. Okay. mod of A prime B prime, this should be equal to modulus of what? Modulus of A prime O prime. This should be equal. Okay? This should be equal. And so let us see here. I have shown it this fact here that yes. Now see this geometry of figure. According to triangle of addition, vector AO plus A dashed O dashed plus O dashed B dashed, that will be equal to A dashed B dashed. So I have written it here. You can see that A dashed B dashed is equal to A dashed O dashed plus O dashed B dashed. Okay. Now let us consider that this vector A dashed B dashed is equal to K dashed. So K dashed is equal to K plus G. And as I have told you that diffraction will occur if the point B dashed must lie on the same surface of the same sphere. This is the necessary condition for occurring diffraction. And for this, modulus of A dashed B dashed must be equal to mod of A prime O prime. But you have seen that A dashed B dashed is equal to vector K plus vector G. So mod of vector K plus vector G must be equal to mod of vector K. Okay. And so if you take a square, then you can also say that a square of the modulus of K plus G is equal to mod of K square. But you know what will be the square of modulus of K plus G? That will be actually K dot K, which is actually K square, plus G dot G, which is actually G square, plus 2 K dot G. But this K dot K is K square, G dot G is G square, so I have written it here that this is K square plus G square plus 2 K dot G, and that equal to K square. Now this K square and K square will cancel out, and your result is G square plus 2 K dot G equal to 0. Actually, this very equation, which is in terms of the reciprocal lattice vector G and the wave vector K, this is the vector form of Bragg's law. This equation 4, which reads as G square plus 2K dot G equal to 0, this is the vector form of Bragg's law. And as I have told you earlier, that this law is used in the construction of the Brillouin zones. Okay. So here you can see that G, which is actually equal to 2 pi times reciprocal lattice vector, and K is 2 pi by lambda, and this is equal to the incident wave vector. Okay. Now you can see, if we treat that this A prime O prime represents the direction of the incident X-ray, then actually this direction A dash B dash, that is the wave vector K prime, represents the direction of the reflected wave or the diffracted wave. So K is in the direction of incident X-ray beam, and K dashed vector is in the direction of the reflected X-ray beam. Okay, reflected wave. But since modulus of A dashed O dashed and A dashed B dashed are equal, so you can say that mod of A dashed O dashed is equal to mod of A dashed B dashed. But A dashed O dashed vector is vector K dashed, and A dashed B dashed is, A dashed O dashed is K, and this is actually K dash. I have written it in opposite side here. So you can see this K mod of K dash will be equal to K. Or in other words, you can say that K square equal to K dashed square is equal to K square. Okay. So magnitude of the wave vector of the incident ray and the reflected or diffracted wave is same. But in vector form, vectorially they are not equal. You can't say that k prime vector is equal to vector k. You cannot say. It means after Bragg's reflection, what happens? When Bragg's reflection takes place, then the magnitude of the wave vector does not change. Only its direction changes. So k dashed is not equal to k, but mod of k dashed is equal to k. And you can see from here that actually the difference of this k dashed vector and k is equal to the reciprocal lattice vector. This is a very important fact that when you will subtract the incident wave vector from the reflected or the diffracted wave vector, you will get the reciprocal lattice vector. Okay. So actually this indicates that the scattering does not change the magnitude of the wave vector k, only its direction is changed, and so the scattering is elastic. When I have taught you the Bragg's law, then I have told that this scattering proposed by Bragg of X-ray due to crystals is elastic scattering. Okay. And also the scattered wave differs from the incident wave by a reciprocal lattice vector g. Okay. So in this lecture you have actually learnt about three things. First of all, you have obtained the Bragg's law, which is a well-known law of crystallography, 2d sine theta equal to n lambda in terms of the reciprocal lattice vector. After that you have learnt about the Ewald construction, and finally we have seen that how we can express the Bragg's law in vector form, okay, in terms of the reciprocal lattice vector. Okay. And from this calculation we have also concluded that due to Bragg's reflection there is no change in magnitude of the wave vector, but there is only change in its direction. Okay, only its direction changes. Okay, and the difference of the wave vector of the incident X-ray and the diffracted X-ray is simply equal to the reciprocal lattice vector. So you can see this reciprocal lattice vector plays a crucial role in understanding the diffraction of X-rays by crystal. Okay. So I hope you have definitely enjoyed this lecture, and this is a very important concept for your examination purpose. So watch the video seriously and write down these things in your notebook, and definitely that will be very helpful to you. Thank you very much.